Welcome to our video on the law of sines. So far we've been dealing with SOHCAHTOA and finding angles and side measurements for right triangles. But unfortunately the world is not made up entirely of right triangles, and we have to be able to deal with the situation when we have a triangle that doesn't have a right angle, and that's where the law of sines, and then we'll also see in another video, the law of cosines, comes in to help us. So some vocabulary. This diagram shows the law of sines. Whether we're dealing with an acute angle or an obtuse angle, we can still apply the law of sines to any triangle. And what I mean by acute versus obtuse is here we're concerned with angle B. And on the right hand side you can see that angle B is greater than 180, and on the right hand side it's less than, so there's obtuse versus acute. Okay, the law of sines gives us a way of figuring out these lengths of little a, little b, little c, and these angles as ratios. So if we know some information, we can figure the other bits and pieces out. And it all really comes down to our regular SOHCAHTOA and a little algebra. So let's take a look at the angle or the triangle on the left. We start with the whole triangle, but we're going to cut it, right? We're going to drop this red line down, H, and we're going to create this new triangle, CBD, right? CBD. And we know that H over A, right? H over A is equal to sine of B, right? If this is opposite over hypotenuse. Now in the other triangle over here in ACD, we know that H over B equals sine of A. And if we solve each of these for H, we get H equals A sine B, or H equals B sine A. Now set them equal to each other, right? Because they're both equal to H, so they're equal to each other. A sine B equals B sine A. Since they're equal, we can do operations to both sides, so we can divide both sides by AB. The B's cancel here, the A's cancel here, and we get sine of angle B over side B, right, lowercase b, is equal to sine of angle A over little a. So we get this nice ratio relationship that sine of the angle divided by the side opposite of it. You'll notice in the picture, little a is opposite of angle A, little b is opposite of angle B, and little c is opposite of angle C. So we're always talking about the side of the triangle opposite that angle. Sine of the angle divided by the side opposite it, that ratio is consistent throughout the triangle. Right here we've just proven that B and A work, but we could very easily drop a red line from A over in the other direction. We could repeat this process with a line like this and create a right triangle here, and then redo the process between C and B. And then once we see that there's a ratio between C and B, then we get C and A right just out of it, because if we have C to B and B to A, then by transitive theory we have C to A. I'll leave that for you guys to do on your own if you really want to prove it to yourselves, but it's a similar, almost identical argument. And then over here, the argument's the same. It's just there's one step that when we're dealing with this angle, we have to realize that sine of 180 minus b is equal to just sine of b, and that comes from sine of x minus y equaling sine x cosine y minus cosine x sine y. Remember the sum and difference formulas? And then because x is 180, we get sine of 180, which is 0. Cosine of 180 is -1. And so we end up getting 0 minus -1 times sine of y, and in this case that's just sine of b, right? The negatives cancel, and that's how we get sine of b. So similar argument on the right hand side with that little substitution, and then we were able to show that sine of b over b is sine of a over a, and there you have the law of sines. Okay? The ratios are the same, and because they're ratios, we can also flip them. We can rewrite them with the lengths of the sides over the angles. And that's very helpful, because if we're trying to solve for little a or little b, it's a lot easier to solve for it when it's in the top of a fraction rather than the bottom of a fraction. Okay, let's see how we can apply this. Here's our first example of solving the angle-angle side and angle-side-angle version. We want to find the measure of the third angle, right, by first subtracting the measures of the two known angles. Because in this case, we're given angle ABC with two angles and one side, and then we want to find all the other bits and pieces. We basically want to figure out what this angle is, and in order to determine an angle, we need to know all 6 pieces. We need to know all 3 angles and all 3 sides. When it's a right triangle, not as much, but when it's not a right triangle, you need all 6. The first thing we can do very easily is solve for the third angle. Whenever you're given 2 angles, you can always get the third. So whether it's angle-angle side or angle-side angle, right? That's what these things up here mean. Angle-angle side or angle-side angle. Doesn't matter which situation you're in both of those you're given 2 angles. You can solve the third one by just knowing that all 3 angles in any triangle have to add up to 180. So that's what we did here with step 1. Step 2, we draw ourselves a picture, and in fact you should always draw a picture as soon as you can and start labeling things. Here we also give ourselves a nice little table just to kind of organize our data. We've got the 3 angles, we've got the one side that they gave us, and now we can go about solving for the other bits and pieces using the law of sines, which is what we're doing here. Remember that the best thing to do with the law of sines is to always keep the thing that you're trying to solve as the numerator, at the top of the fraction. So if we're trying to solve for b, we can do b over sine b equals c over sine c. Now why did we use c and sine c? Because they gave us c, right? They told us one side was 14. That was our known side, so that's the one we have to use. Then we solve for the missing piece, right? We have all 3 of those pieces because we know what b is, we know what c is. We can find sine of 74 in our calculator, sine of 44 in our calculator. So we have 3 out of the 4 pieces. We can always solve for the missing fourth. There it is, 19.4. Now that we have that, we can go back and solve the other one. Not by Pythagorean theorem, that doesn't work because we don't have a right triangle. We have to go back and do the law of sines all over again. Now we could use the new one. We could do a over sine a equals b over sine b now that we know b, or we could stick with the original c and sine c, and the only reason why we would do that is because 14 is an easier number to work with than 19.4, and it happens to be a precise number, right? 19.4 we've rounded, so it's better to always use the precise numbers if you can. Then you solve for the last piece of 17.8, and there you have it. You now know all of the bits and pieces. You have the 3 angles. You now know that b is 19.4. and A is 17.8. And you're done. Okay, how about an example that is kind of more of a word problem, where from some point on a level plane at the foot of a mountain, a surveyor finds the angle of elevation to the peak of that mountain to be 20 degrees. Then the surveyor walks 3,465 meters closer, right, on a direct line, just meaning, straight towards it, and finds that the new angle of elevation is 23 degrees, and now we can estimate the height of the mountain to the nearest meter using those two measurements. First thing we should do, draw ourselves a picture. We started at point A, we had an angle measurement of 20 degrees. We moved 3,465 meters closer to the mountain, got a new angle measurement of 23, which gives us the angle of B is 157. And then, of course, using 180 as our total, we can solve for C as being 3. And now we have a triangle, right, that we can use the law of sines on. That triangle right there. So there's our picture still. If we're trying to find this measurement here, this A, we know that A over sine of 20 has to equal 3,465 over sine of 3, and then we can solve for A. And now that we have A, we have the hypotenuse of this right triangle, right? Because our ultimate goal was to find the height of the mountain. We need to find H. We use the law of sines to solve for the hypotenuse. Now in that triangle BCD, right, this angle, or this triangle BCD, is now the right triangle. We can go back to this angle here and know that sine is opposite over hypotenuse. Sine of 23 is going to be H over A. Sine of 23 is just a number. We can do that in our calculator. A we just solved for, so we can find the missing piece. Multiply both sides by A. So now we have H equals this. Plug in our A, figure out sine of 23 in our calculator, and we get that the height is almost 8850, right? 8848 meters high. How about an example where we're dealing with sine, sine, angle? In the previous two examples, we had two angles and a side. Now, I believe I'd said sine, sine angle instead of side, side angle. Now we're dealing with two sides and an angle, and that becomes the ambiguous case. Ambiguous is a big fat word meaning we're not really sure. We can get different answers. If we know the lengths of two sides of a triangle and the measure of the angle opposite one of these sides, please take note that this is different, right? This is side, side, angle, which is different than side, angle, side, where we know the measurement of two sides and the angle in between them. So this part of the triangle is etched in stone. A, B, and then angle C we know, and because we know this, there's only one way to finish it off. This length here is now etched in stone, because if these have to be a set length and that's a set angle, then that's going to be a set length in between. There's no other way to do it. But when you have side, side, and then an angle, so you basically have a side, and then you have a third angle, right? This is now what you know. A, B, and then this angle here, which we would actually call A, right? Because it's opposite little a. Now, different things can happen. And you'll see. Here are our cases. Remember, we know A, B, and angle A. Okay, we start with side, side, angle. So we were given A, B, and then the angle A. If when we draw the picture and create a right triangle out of it, if A, the length of A, is less than H, which we know is the shortest distance between C and the horizontal axis that's created by the other half of A, then we can't get a triangle. A is too short. No matter what angle you let C be, right? If you can imagine the end of A is a pendulum and it can swing back and forth, it's never going to come down here and touch because it's too short. So no triangle if it's less. If it's exactly equal to it, we get exactly one triangle because it's only going to touch in that one place. If A is bigger than H but smaller than B, right? So its length is longer than H but smaller than B. It can swing, and you can see that as it swings, it's going to hit in these two spots. And it's going to create two triangles. Either this one here, right? Or this larger one there. Two different triangles. Another case, if A is bigger than B, right? It's already bigger than H, but now we're just going to make it bigger than B. Then now it's so long, once you make it one length, it's only going to touch in one place. Because if you take this and start swinging it in that direction, you see how it's going to lift up off and it's not going to touch. It's just going to keep getting taller. And then if you swing it in this direction, it's going to come down here and then it's going to come around. It's going to come around and it's not going to touch again until way over here. Right? Come all the way around and touch over there. And then you no longer have angle A. Right? You no longer have this side here attached to that side, creating that angle. So this contact over there is invalid, doesn't work. You only get one, so you're stuck with just this shape instead. Now all of that was when A was an acute angle, so angle A was less than 90. Now when angle A is greater than 90, we have two more cases. If A is less than B, no triangle. If A is greater than B, we have a triangle. If A was this equal to H thing, it wouldn't work, right? Because now A is obtuse, and remember H would be over here to create a right triangle. And so if it was equal to that length, it would just come down here and it wouldn't touch. The only way it could touch would be over here, but again that wouldn't work because then we wouldn't be using A, we'd be using this angle over here. So put all that together, you've got all these cases. If A is an acute angle, we get 4 cases. If A is an obtuse angle, we get 2 cases. So all in all, you have 6 different cases ranging between no triangle, 1 triangle, or 2 triangles. Please don't waste brain energy trying to memorize all this. Just have this slide handy, have it in your notes for the few homework questions that you might have where they just ask you to find the number of possible triangles, like this one here, right, where they want you to figure out how many possible triangles you could have, or this one here, again, where they want you to figure out how many possible triangles you could make, and it would just be a matter of looking at your table. But what's more important is actually solving these things. So don't worry so much about how many you might have. Just know that there is a possibility of 0, 1, or 2, so you have to keep that in mind when you're trying to solve these things. Okay, look at an example here with side-side angle. They give us triangle ABC. They give us the angles of B, right, and the sides of B and C. I've drawn my picture. You might ask yourself, how do you know ABC looks like that? I don't. I just draw a generic triangle, ABC, right? So just any triangle, label it ABC. I could have labeled it ABC in the other direction. It really doesn't matter. I just know that B is 32, and I know that The sides, remember, are always opposite the angles. So this side is angle or side A because it's opposite angle A, and so on and so forth. So it tells me where my two sides are, and you can see that I have a length of a side, a length of a side, and then an angle attached to that second side. So there's my side angle. Side, side, angle. Fill out a table, right? Just put our information in there if you want to. Not really necessary, but it's just helpful to keep everything kind of organized. Okay, step 2. Apply the law of sines to the two ratios that we're trying to find. Right? We need to find A. So we would need to do A over A, or A over A, right, little a, but that doesn't work because we don't know either one of those two pieces. So the only ratios we can work with, this one, because we know both of those pieces, and this one. Using that law of sines, we can solve for this missing piece, and then once we have this missing piece, how do we solve for A? Well, we just know those add up to 180. Okay, so we're going to have angle C, sine of angle C over 150 is going to equal sine of 32 over 100, and now we can solve for C. Multiply both sides by 150. Sine of C equals 150 sine of 32 over 100. This is going to give us a number, right? Just plug this all into our calculator, and then to find C, we're just going to do inverse sine of whatever that number is, which is what we're doing here. And we get almost 0.8, right? 0.7949. Now, step 3 is we have to check this. This angle that we just found, if the sine of that angle, right, if the sine of that angle is greater than 1, then there's no such triangle with the given measurements, right? In this case, we stopped short of taking the inverse sine. We just found that sine of C is going to equal this number, and we know that our sine function has a domain between -1 and 1, right? Sine, our normal sine function is between -1 and 1. So if this number here, I'll highlight it, if that was bigger than 1, it's basically asking an impossible thing. There's no solution. So there is no angle, there is no triangle. But because it's in our range, it's good to go, then we can move on and actually solve for it. The only reason why they're saying it has to be between 0 and 1 is because you're not going to find a negative distance, right? Okay, so now that we know that it exists, we can solve for theta. We're looking for this sine theta, which we saw before on the previous one. Sine theta equals 0.7949, and it's in between 0 and 1. If x isn't equal to 1, then theta has two possible values. Well, it's not equal to 1, right? So it's got two different possible values. Sine inverse is going to give us the angle that's between 0 and 90, and then we can also kind of do the negative version, right? 180 minus it and get the other angle. So here are our two results. We do inverse sine of this and just get 52.6 degrees, and then we know that 180 minus that, there's the other angle. And you might be asking yourself, how the heck do I know this? Where does this come from? Well, remember, if we have an angle here, theta, sine gives us this distance here, right? Sine of theta is going to give us that height. But couldn't we also go 180 degrees minus this same theta and then we know this height here is going to be the exact same height. So that's what we're doing here. We're doing 180 degrees minus that same 52.6, and then therefore sine of these two angles will give us that same height. Okay, back to our picture. Once we found our two angles, remember 52.6, 127.4. Here's the two angles, 52.6, 127.4. If you recall, and if you don't, you can go back up and see that the other angle B was given as 32. And when we add those two together, they're less than 180 in both cases, so that means both of them are legitimate, right? They're possible. We can actually create a triangle with those. What would have happened if this secondary angle was 152? Well, then when you add it to 32, you get something that's 184, which is impossible, right? Because the third angle has to add up to 180. So now that we check that, we know that there actually is a third angle for both of these, 95.4 and 20.6. And now that we found those, let's draw a picture just to remind ourselves. We have one triangle, and don't bother that they're not accurate as far as their shape. Okay, here's my two triangles. We'll call it, it was A, B, C. In this triangle, we were given, I believe, B, 32, 32. Here we solved for it, and we had 52.6 and our third angle would be 95.4. Yes, I know these angles are not nearly the right shape. Over here, it was 127.4, and so we had 20.6. They also gave us, I believe, the side opposite B, right? Let's go back up and remind ourselves. We had 100 for B and 150 for C. 100 for B, 150 for C. And now you can see that we can solve for this unknown A in both triangles. Right? Now you might be thinking, hey, if I use little b over sine of b and equate it to little a over sine of 127.4 for this triangle, and then I go up here and I do little b, right, over sine of 32 is little a over sine of 52.6, you might think, aren't I going to get different responses? Well, let's see. So here's the first one, where we're using the 95.4 triangle. We get 187.9. Here's the second one, 66.4. And so yes, we did get different responses because, as we knew, when we're doing side-side angle, it's possible to get two separate triangles. So it's a nice idea to use these little tables and just keep your information separate for the two triangles. Here's my first triangle, BAC, with all of those lengths and measurements, and then here's the other one with the other lengths and measurements. You can see that the only things that are the same are the things that were given to us: 32, 100, and 150. 32, 100, and 150. Everything else changes. We get two completely different triangles. And here's the picture of the two triangles. This is that angle, or sorry, this is that that length here. These two sides, these are both side A, and all that's happening is the pendulum is swinging, right? It's swinging, and it's attached, it's hitting these two places, and when it hits here, we get the outer triangle, and when it hits there, we get this little smaller, obtuse one. Okay? If we look at another example with side-side angle, this one has no solution. Okay, so we make our chart. We recognize that we have one complete ratio and one half ratio. So that would be the first thing that we would have to solve for, right? Draw your picture. Doesn't matter what it looks like. A, B, C. They give us this is 50 degrees. This is an 8. B is 15. Right? C we don't know. But we can solve for angle B. We know that sine of B over 15 is going to be sine of 50 over 8, or sine of B equals 15 sine 50 over 8. When you do that math, as we've done over here, you get 1.44. And because that's bigger than 1, we know there's no such thing. There's no angle that we can take the sine of and get an answer that's bigger than 1. So no solution. Here's an example with one solution. I'm not going to spend a lot of time on this one. I think you guys get the idea. Step 1, make your chart. I would also draw a picture. Pick out the things that you know, right? You know C and C is a full one. A and A is your half one. So that's going to be your first step, is solving for the other half piece that you don't know. Do all that. Get your two possible values. Since one of those two possible values ends up giving you a combination of angles that's greater than 180, we know that's impossible, and now we only have the other one as a possible solution. So we continue on with that one to solve for the missing third piece. And there is our final table and picture. Okay, so those are side-side angles. After that, the other thing we deal with when we're dealing with these types of triangles is bearings. And you just need to know that when we're talking about a bearing, we're talking about an angle measurement from either due north or due south. So going north and then 40 degrees east is just the angle from the y-axis 40 degrees to the right. North 60 degrees west is just going 60 degrees to the left of north, right? And then we could also do the same thing with south. South 30 degrees west versus south 75 degrees east. Once you know what it means for bearings, you can apply side angle, side angle side, angle angle side, whichever situation you have, to a word problem that deals with bearings, like this one. We have a ship sailing due west 20 miles per hour. The bearing of an oil rig at north 55.4 degrees west. An hour and a half later, they take a bearing to that same oil rig and they get north 66.8 degrees east. They want to know how far is the ship from the oil rig the second time when they take that second measurement, and then how close did it pass the oil rig. So draw yourself a picture. Dot C is the oil rig. Dot A is where they started when they took their first bearing. Remember, their first bearing was north 55.4 degrees west, and that creates that side here, right? B. Then they move along. They were doing 15 miles per hour, and it was, 20 miles per hour, and it was an hour and a half later, so that's why this is a distance of 30 miles. Now they're over here, and when they look back and see the oil rig, they now have a bearing of 66.8 degrees to the east of north, which delineates that right? Angle and side. And from that, we now know these two angles in there, because if this is 55.4, this has got to be 90 minus that, or 34, right? 0.6. And then this one has got to be 23.2. Now we know this angle, because it's going to be 180 minus 23.2 minus 34.6. We know this length here, so we have a full full ratio of angle C and its length, and we have a half ratio with both the others, so we can solve for those two lengths for sure. And then once we have all that, we can solve for the h here in between. Okay, these are the two angles that I showed you, the 34.6, 23.2, the third one, 122.2. We can use that complete one with C to solve for the A piece. And then we get A is roughly 20 miles, so the ship is approximately 20 miles from the oil rig when the second bearing is taken, because that was the first question. So now we go back to our question, or sorry, back to our picture, plug in what we know. This was roughly 20. This was 122.2, right? This angle down here was 23.2. If this is 90, we can now solve for this missing piece there, but we don't really need it because we know sine of 23.2 is opposite over hypotenuse, right? And when we plug in all the bits and pieces that we know, in this case, this is 23.2 goes over here, duh. And then opposite over hypotenuse, because that's the one we solved for. We didn't solve for this one, so we want to use this one over here. Plug in everything we know, and we get this H distance of 7.9, or they came a little less than 8 miles from the oil rig as they were cruising along. Last but not least, we can find the area of an SAS triangle, and this only works for SAS, with a very simple formula. Again, don't try and memorize this, just put it in your notes and just use it whenever you have a homework question or something that deals with an SAS triangle and finding the area. Something like this, find the area of ABC given side, angle, side, right? Can you recognize how this is side, angle, side? They gave you a side and an angle and a side, and that angle's in between those two sides, right? It's the angle that's attached to those two sides. So that's side, angle, side. Plug all your bits and pieces in, and there's your area. Okay guys, that's everything we need to know for the law of sines.